Hello everybody, thank you very much for joining us here today. This is Paul Taubman with 9.Connects. You are in the right place if you are here for our presentation titled The Stuff That Makes Up Signal Integrity, also known as AC Impedance. This webinar will build off of a prior webinar titled What is Meant by a 50 Ohm Impedance. And before I turn it over to Sean Kelly, our expert in RF and high-speed design, I do want to note that we will not have time for questions during the webinar today. In fact, it will run the full hour. However, if you do have a question, please feel free to write in the questions region of the panel provided by GoToWebinar. And if you are going to do so, we ask that you be specific so that we can respond to it without difficulty. And we will write up our customary Q&A for the webinar afterwards, which we'll make available to you if you'd like to have it. And with that, I will turn the comm over to my colleague, Sean Kelly.
Hello everyone, thank you very much for taking time out of your day to join us on this deep dive today. We're going to talk a little bit about last month's webinar to do a little review because of what we're doing is building off of that information. In the last lesson titled, What Does a 50 Ohm Impedance Really Mean?, we discussed what makes a transmission line behave in a way that the source sees a 50 ohm impedance. In that discussion, we only talked about the charging of the line. That is a DC analysis. Specifically, there were three things that we got from the last webinar. Transmission line propagation, in that it is wave-like. We talked about characteristic impedance, and we talked about a transmission line with a load. The transmission line propagation. What we did is applied a step voltage, and we froze the circuit for an amount of time, and we talked about it. If you freeze time just after we applied that step voltage and you took a voltmeter and measured the voltage at different points along the line, you would see a graph of points that form a wave. The more positive voltage will occur on that part of the line where the forces have been able to reach in the short time. As the time continues, the distribution of charge continues so that the voltage differential appears to propagate to the right. The second thing, characteristic impedance. You'll notice that we have the standard characteristic impedance equation in the upper right-hand corner. The proper way to think about a transmission line is that it's a series of subset inductances and capacitors that are distributed equally per some unit length. Any transmission line can therefore be thought of as L henries and C farads per inch. The characteristic impedance is a function of the ratio of that total inductance to total capacitance, or you can think of it as the ratio of per unit length inductance to per unit length capacitance. A transmission line with a load. This is a repeat circuit that we talked about last time. If we take a simple two-port circuit, being a transmission line, it's here in the red square, and we use it to feed a resistive load of 50 ohms. Then we picked a right ratio such that the characteristic impedance is also 50 ohms. Then we apply a voltage source, and for a very short time that inductance is going to impede the sudden change in current used in charging of the capacitance. The capacitance starts to charge up to V. As the capacitor charges, the load resistor will start pulling current. At the point the capacitance is fully charged, the current through the inductance becomes steady. For the source, it is always going to think it's connected to a 50 ohm resistor. Think of it this way. As the current in the capacitive leg decreases, the current in the resistive leg is going to increase in direct proportion. Therefore, the source sees only one current value to reach during the transition from T0 when we apply the step voltage. In conclusion of the prior material was to understand that the transmission line characteristic impedance is a way to describe the T line as an intermediate load as seen by the source. The characteristic impedance is not really an impedance as much as it describes the way it behaves. In AC analysis, the T line is seen both as a load and a source, an intermediate load to the source and a source to the final load. In the end, the transmission line has one goal, to allow the maximum amount of power to get from the source to the load. Now the difference in AC wave behavior and the DC analysis is that the line not only charges, but it's also going to discharge and then charge back to reverse polarity and then discharge again. This behavior can take on many different shapes. We're going to talk about sinusoids primarily today. We were not going to talk about trapezoids, but they are sometimes used. And then the square wave, which is ultimately going to be the crux of what we're going to talk about today. When you're thinking about AC wave behavior, you have to think wave, not current. So what I've shown you here is the propagation of a wave going down a microstrip. From the top on the left and on the right, you can see within the microstrip in the bottom third of the structure, and the top 2/3 is above the microstrip. You can see most of the energy is captured below the microstrip in the substrate. Now, this AC analysis is going to be easy to demonstrate visually using a sinusoid. So that's why you can see that there is somewhat of a sinusoidal pattern to this. But to understand AC analysis and its effect on high-speed digital design, we have to talk about a square wave. And in doing that, we're going to have to talk about the frequency content specifically. When I first got into electronics as a technician, I really only understood the concept of a time domain signal. In other words, what I could see on an oscope. What I didn't understand until I took EE classes was that time domain signals had a corresponding frequency domain. As a voltage changes in time, it does so because there exist specific frequencies with specific power all at the same time in that same circuit. It's a concept called superposition. So if we look at the ideal square wave in blue in this picture, you can see that the realistic composite of all the different frequencies is going to be this red waveform that you see with a little bit of ripple in it. This is the real life type of square wave that you're going to see on an oscope. Now, to get that, you're going to have different frequencies. Now, this picture shows you that if you assume that your fundamental frequency, which is the same as your square wave, is at 100%, then you're going to have other frequencies in this descending amount of power relative to that main fundamental. So, for example, and you're going to learn more later on that this is actually the third harmonic. So if this is 1 gigahertz, this would be 3 gigahertz. And you're going to see that there are 3 of the green waves within one cycle of your fundamental, and so forth and so on. So the purple is the 5th harmonic, the pink is the 7th, and so forth and so on, and decreasing power levels. The frequency domain refers to the way one looks at signals based on the frequency content. People typically will use a spectrum analyzer to see what frequencies exist on that node or in that circuit. A network analyzer is a tool that measures the effect on specific frequencies a device will have. We'll talk a little bit about that later on. The two domains were the same thing, but just a different way of looking at something. You can look at a square wave with an oscope and see one thing, and on a spectrum analyzer and see another. But in reality, they are showing you the same thing. Mathematically, every perfect square wave is composed of the fundamental frequency and odd harmonics of it in descending power levels. Before we go any further, let's do a real quick review of some definitions. A decibel is a logarithmic unit used to express a ratio of two values, and in the following discussions, those units are typically going to be power. It is a little bit easier to understand dB if you understand that a change in power by a factor of 10 corresponds to 10 dB. A change in the power of a factor of 100 corresponds to 20 dB because we're talking about log base 10, so we're talking about a power of 10. Therefore, a factor of 1,000 would be 30 dB, and so forth and so on. The concept of attenuation is a measurement of a loss. It typically is measured in decibels also. We're also going to talk about later on is an eye diagram. So when we get to that point later on, this is an idea of an eye diagram where a test signal is run through a circuit, and so we see alternating zeros and ones, and we see how open that this area is in the middle. So mathematically, when we're discussing the content of a square wave, there's a term called a Fourier series, and it is a means to describe the time domain signals in the frequency domain. So we have x as it varies in time is a function of these frequencies. And when you expand out this series, for those of you who may not be familiar with it, we start out with a series where k equals 1, and then we keep increment it all the way out to infinity. So every time k goes from 1 to 2 to 3 to 4, we end up with multiples of this term right here, the 2 pi f, 6 pi f, 10 pi f. The first term, 2 pi f, is going to be the fundamental frequency. It is referred sometimes as the first harmonic. The second term is a 6 pi f. It's the third harmonic. The third term, 10 pi f, is the fifth harmonic, and so on. But for all intents and purposes in the real world, anything past the seventh harmonic is not really relevant. Now, I'm going to be using an applet that I'm giving you a link to that we can use to take a time domain signal and find out the frequency content. Really handy little applet. I'm not going to use it today, but I've captured pieces of it in this presentation for you. The first thing I want you to understand is that the frequency of the square wave is not important in this demonstration. One of the reasons why I bring this up is because the applet itself has a limited frequency that it can use. The thing you keep and understand is if I pick 1 kilohertz in the applet, then it's the same concept frequency-wise as 1 gigahertz. You just change the power. The relationship between the spectral content and the fundamental frequency of this discussion is always going to be the same. Mathematically, every perfect square wave is composed of the fundamental frequency and odd harmonics of it in descending power level, and that's what the applet is going to show you. So if you go to this website and you pick a square wave, this is the first thing you're going to see. So let's take a close look at this applet while keeping the superposition image in mind. Using the default number of terms and the default magnitude of each harmonic, you can see a great square wave. Looks almost perfect. Notice though that all the even harmonics are equal to 0. So when you're looking at here, here's your fundamental, here's the power level of your second harmonic. This would be the power level of the third harmonic, fourth, and fifth. So notice you only have the odd harmonics. Now if I reduce the number of terms, notice you start seeing more ripple because those other harmonics that were even higher were used to smooth that out. What you're seeing is a result of a low-pass filter. Notice also how the slew rate has decreased. No longer is the vertical change almost completely vertical. So if the fundamental is 1 gigahertz, then we are looking at up to 9 gigahertz being needed for just this amount of defined shape. So if I take a fundamental, which you see there in yellow, at 1.27 the magnitude, you'll notice I also have in the graph there that it's at 1.024 hertz, or basically 1 kilohertz. But again, that isn't that important to understand. The third harmonic is at 0.4244, and the fifth harmonic is at 0.2546. Now these are all the same weightings that that previous graph showed you. Notice you have not too bad of a looking of a signal. A little bit more ripple because we're only looking at the third and the fifth harmonic. Now we're going to start the concept of the low-pass filter. If I take a soft attenuation curve, you can see that there's less ripple is present, but the slew rate is even slower. The net effect is closing that eye that we were talking about earlier in the eye diagram. The eye remaining open now becomes even more dependent on the minimum attenuation of the fundamental. In this situation, I reduce the third harmonic by 20% and the fifth harmonic by 50%. Now if I take a really steep curve and I do a 3 dB cut to the third and a 6 dB cut to the fifth, I'm causing a reduction of the third harmonic by 50% and the fifth harmonic by 75%. You can see that the net result as a square wave is almost back to a sinusoid. Now, one thing that this doesn't even consider is jitter. The eye-closing dilemma doesn't take that into consideration in this discussion. Jitter is the side-to-side movement of the waveform due to instabilities of the signal generation circuit. So, imagine this diagram here moving back and forth. You could see that the eye diagram is going to close even more. This exercise is to show the effects that circuitry exhibiting low-pass filter behavior has on a square wave. Now, serial data is not a continuous square wave. We know that. But it is an asymmetrical version of one. Serial data could have some portions of it being composed of that fundamental square wave. In conclusion, any portion of a transmission line that creates a low-pass filter is going to be detrimental to high-speed designs. That's the thing I wanted to point home to you on this portion. So the next area of this webinar, we're going to get into scattering parameters, because we have to have some way of characterizing these transmission lines. S parameters is a concept used primarily by RF engineers. The history comes from light engineers. They used it originally to explain light behavior when going from one medium to another. Generally used to define behavior reports connected to matched loads. Quantities are measured in power of units, or units of power. It is a universal way to describe the loss of a circuit related to frequency. So you may be asking, why use scattering parameters? Because most of us have taken circuits class and we learned what a two-port network was, and we learned how to do analysis based upon current and voltage. Not a problem as long as you're working in low to medium frequencies. But as operational frequencies get higher and higher, this method won't suffice. Equipment is not readily available to measure the total voltage and total current at the ports of the network. Short and open circuits are difficult to achieve over a broad band of frequencies. That's really important to understand, because most of the time when you're talking about transmission lines, you're talking about a very broad band that which you want that transmission line to be well behaved. The solution was to describe a network in terms of a traveling voltage wave and their power rather than total voltages and currents. Going back to our analogy, there we thought of charges moving on inductors. This in turn created a wave-like behavior of the voltage and current. Continuing with that analogy, then there's going to be a wave going into port 1 and a wave coming out of port 2. So let's discuss the incident waves. You're going to have an incident wave going into port 1. We call that A1. We're going to have a wave leaving port 2 that we call B2 that's going to be incident on the load. When wave A1 goes into port 1, any impedance mismatch will cause a reflection that we will call B1. When B2 leaves port 2, any impedance mismatch of the load is going to cause a reflection of B2 back towards port 2. We call that wave A2. Now I know I've been throwing around a lot of terms, but the main thing to get from this is when you're looking at a two-port network, you have two inputs. You have the A wave is coming in from your source, and the A2 wave is coming in back from the load. Based upon this one, the impedance mismatch. The outputs are labeled a B. You have an incident wave going to the load, and you have a reflected wave going back to the source. The output signal B2 is ultimately a composite of voltages coming in from port 1, that is wave A1, and any voltage being received back from the load. Likewise, B1 is also a composite of voltage coming from port 2, that is wave A2, and any voltage being reflected by port 1. Mathematically, these outputs, B1 and B2, can be expressed as a sum based on what is called scattering parameters. It is important to understand the physical relationship of A1 and B1 being on the same port and not as shown. So I want everyone that's looking at this diagram to understand we're not talking about two different wires here. We're not talking about two different terminals. We're talking about this is one port. The port has both A and B on it simultaneously. Now, the thing we need to understand here is that we have the complete flow graph for a two-port network, and it shows you the physical relationship of how the scattering parameters describe the behavior of the waves as they relate to input and output. That's how we're going to come up with this equation over here is to the outputs B1 and B2. So looking at this nice pretty graphic here, you can understand that if I have an incident wave coming from a source A1, it's green. As it comes through my transmission line, it is going to be characterized as how well it gets through my transmission line by a parameter called S21 and then get on the output as wave B2. But also notice that this arrow has two colors to it. That's because if you'll notice up here in this diagram that B2 is a function of the S21 times A1 and S22 times A2. Because if we have a reflected wave coming back to this port as A2, then part of that is going to interact with the wave coming from A1. So you're going to have a summation of these two voltages creating B2 right here. Same thing back over on port 1. We have the incident wave comes in to the transmission line, device under test. But if there's an impedance mismatch right here, then what ends up happening is this S11 characterizes that mismatch and gives you part of A1 to be reflected back toward our source. Hence, B1 is a combination of that reflected energy along with the energy coming back from the load. So B1 is actually a double whammy, so to speak. Keep in mind that in a perfect world, there would not be any impedance mismatches. Therefore, A2 would be 0. In other words, my load would not create any reflection. And S11 would not exist because the impedance of my source is going to be matching the impedance of my transmission line. Under those two conditions, we end up with B1 ends up equaling 0. So in other words, the source never sees a reflection at all. Also, B2, which is going to my load, is only going to see the ability of my transmission line to pass A1 wave. That's what we're shooting for in every transmission line design. Before we go any further, again, it is important to make perfectly clear that in the diagram below, we are not looking at terminals. It's talking about waves as they relate to ports. Both B1 and A1 are on the same terminals. Both B2 and A2 are on the same terminals. Let me put it this way. When you first learn circuits, you don't necessarily think about the current as it relates to two different lines at one time in the circuit. You think about it leaving the one node on the source and it goes through a series of impedances and it comes back on another trace. Well, you got to not look at the way high frequency circuits work like that. The positive and the negative are related to each other in physical space. More on that later. So another way to look at the setup is with the network analyzer. If you'll notice here we have a blue representation of the network analyzer. We have a piece of coax going to port 1. And we have both A1 and B1 on that port. Notice that there are two terminals on both ends of the coax. Port 1 of the device under test also has two terminals. Both waves, A1 and B1, travel and therefore interact on this same medium. The same goes between port 2 of the device under test and port 2 of the network analyzer. Now let's take a practical example of a microstrip transmission line. Here you see something we had earlier in the previous webinar, we got a transmission line with a reference plane. The left side of the microstrip has two terminals. Both are part of and make up port 1. The source creates wave A1 and it travels between both conductors to enter the transmission line. Again, going back to what we learned when we first learned circuits, we think about, oh, the current just goes through this line and then comes through here, goes through this load, comes back to this line, back to here. You have to get away from that concept. You have to think about there is energy as a wave on both of these conductors traversing toward port 1 at the same time. The physical relationship of this wire and this wire is very important. The wave travels down the transmission line and leaves port 2 as a wave B2 from both terminals. If there's a mismatch between the impedance of the source and the impedance of the transmission line, then some voltage is reflected back at B1. So in other words, if this transmission line edge here, port 1, is not the same as this internal impedance of my source, there's energy reflected back. If there's a mismatch between my transmission line and the load, the same thing happens. The load is going to reflect back wave A2 back to port 2. So what exactly is a scattering parameter? A scattering parameter is a ratio of one voltage to another wave's voltage. Just like in basic circuits where we learned V21 was used to describe a voltage on node 2 relative to node 1, so goes the scattering parameter notation. The only thing to keep in mind comes from the signal flow graph that we showed earlier. You need to keep in mind every wave is a composite of 3 different variables. Each parameter is created / measured with keeping the third variable as non-contributing. So in other words, if I'm trying to figure out how does this transmission line behave and I want to know what this number is here, S11, notice the equation says that I want to look at wave B1 relative to the wave A1 which is coming in, but I don't want any contribution from wave A2 because S11 is supposed to describe only that amount of energy or voltage waveform that goes from A and comes back out as B from that port. So that's basically what all these different equations give you is the parameter that you see here. 2,1 is a forward coefficient. Again, I don't want the contribution from A2 here to create part of B2. I want to measure what is B2 relative to A1 only based upon how well does the transmission line allow A1 to go through it. So again, that's that discussion up there. The matrix describes mathematically the behavior of the transmission medium or that device. This is a matrix algebraic representation of a 2-port S parameter. So if I want to find B1, you can, or B2, you find it in terms of A1 and A2 and how they relate to this matrix. The scattering matrix can also be used in a variety of other ways. Along with calculating the 2-port wave voltages, it can be used when there are multiple devices in series so that you can combine the different devices into a single matrix. This is done all the time in simulations. If I have a transmission line that has to go through a filter and then out of the filter to a different type of transmission line, you can combine the individual S matrix of all 3 portions into one single matrix. Now, we got the overview done, so let's talk specifically about the individual parameters. The S11 parameter is referred to as a reflection coefficient, gamma. It characterizes the amount of voltage reflected from port 1 back to the source. Ideally, it equals 0. That is when the load impedance equals a source impedance. The range of S11 is going to be between -1 all the way through 1, based upon port 1 impedance being greater or lesser than the source impedance. Below you can see the equation for gamma. When the transmission line impedance is greater than the source, then gamma is positive. When the transmission line impedance is less than the source, then gamma is negative. Two things to keep in mind: open circuit gamma. So in an open circuit, your load impedance is going to be infinity. So you end up with infinity over infinity, which equals 1. For a short circuit, your load impedance is 0. So you're left with minus your source impedance over the plus source impedance, which ends up being a -1. The reflection coefficient is used to develop a very common term called return loss. The input return loss can be thought of as a measure of how close the characteristic impedance of the device under test is to the nominal system impedance. Now, typically in test setups, that nominal system impedance for most of us RF guys is 50 ohms. S11 in terms of power is given by this equation right here, and it represents the power of the reflected signal if you square the magnitude of it. Notice though that this term here is a reflection of the power reflected over the power incident. The magnitude of S11 power can be expressed in dB. Notice here that the basic equation is 10 log base 10 of the magnitude, but because this is squared, you can move the 2 over here to create 20, and that removes the square of this term. Understand this yields a negative number. This is important. Return loss, however, characterizes power loss, but the return loss is a positive number. Because we want to know the loss of the circuit, we want to characterize the inverse of S11. So the inverse of 11 looks at the power of the incident wave relative to the power of the reflected wave. This leads to the following equation, where we have the return loss is minus 20 log base 10 of S11 in dB, and it's a positive number. So what I did is I created a little chart to help you. So if you decide you want this presentation where you can create it yourself, the whole thing easy to help understand these relationships. So again, S11 ideally is 0. So we start at the top of the chart, and worst case scenario, we have an open here at the bottom. So if we start out near 0, you'll notice that the magnitude of S11 starts out negative and goes towards 0. Now, the return loss, however, in an ideal situation, the return loss is going to be infinity. Well, I can't describe infinity here, so I went pretty close to it, and you'll notice that it's 60 dB. As I get further and further away from the ideal situation, you'll notice my return loss gets closer to 0. So what you're trying to understand here is the more loss there is for the S11 means that there's less reflected energy. Now, if you notice in this last column, we have this term called VSWR. VSWR we're going to talk about in just a minute, but basically you understand that ideally VSWR equaling 1 is what you're shooting for. Now, I talk about the positive and negative because the way the simulators express return loss, it's important. They typically express it as a negative number. So when you're looking at graphs, don't confuse the fact that they may be showing you that return loss is a negative number. It doesn't matter if it's a negative or positive in the graph. Just understand the bigger the return loss magnitude-wise, the better off you are. Now, this concept of a voltage standing wave ratio. It is a very common way to express how well matched a load is to a source. It represents the ratio of a maximum voltage amplitude to the minimum voltage amplitude. You can see the equation below. Notice also that it has a relationship with gamma in the equation. That's the reflection coefficient, because ultimately that reflection coefficient is what's going to determine how much you have being reflected. Hence we have the signal, this equation here, the gamma shows a relationship between the reflected signal and the forward signal. Now, let's take an example. If we take the VSWR value of 1.2, it denotes an AC voltage due to standing waves along the transmission line reaching a peak value of 1.2 times that of the minimum AC voltage along the way. So you can see very quickly you don't want a very high VSWR. The second term that we want to talk about is S21. This is the forward measurement. It is called insertion loss. When two measurement ports use the same reference impedance, the insertion loss is the magnitude of the transmission coefficient, that is S21, expressed in decibels. By the way, it is also a positive number. It is given by the equation below. So what we're talking about is I want to know how much B2 is going to be there when A1 comes in. That's what the S21 is going to show me. When I convert it to an insertion loss, obviously we don't want any loss in this forward movement. So you would normally want this to be 0. Now there's going to be extra loss produced by the introduction of the device under test between the two reference planes of the measurement. That extra loss can be introduced by intrinsic loss within the device under test and or mismatch. In case of extra loss, the insertion loss is defined to be positive. S22 is on the port 2. This is the return loss, the reflected wave from the load encounters. It specifies a contribution that A2 has to B2. So again, we have A2 as an input. I want to know B2 here. So S22 is how much energy is going to be contributed back to it. S12, this is the insertion loss A2 is going to see as it goes from port 2 up to port 1, or to port 1 from port 2. It's a very important concept here to understand. If a transmission line is the device under test in this diagram, it is symmetrical, uniform, and homogeneous in construction, then you have S21 is going to equal to S12, and you're going to have S22 is equal to S11. Now, so what is the impact of a lossy line S21? The dB scale is logarithmic, and so even a small insertion loss can be significant. Also keep in mind, in the bigger picture, when you're talking about high-speed data going from point A to B in a circuit, you're going to have a loss budget. Connectors contribute a certain amount of loss. Your transmission line creates a certain amount of loss. The other connector on the other side creates a certain amount of loss. So every one of these is going to contribute to the overall insertion loss. And so you're going to try and minimize the contribution from each piece of this puzzle. Typical simulations will show that the insertion loss is going to increase as the frequency increases. This will impact the amount of higher frequency content that makes it through to the load, going back to this concept of a low-pass filter. As previously shown, this reduces the ability to have fast slew rates and therefore closes the eye diagram. Lossy transmission lines distort the eye pattern because there is more loss at the higher frequencies than at low frequencies. Alternating zeros and ones will be attenuated more than long stretches of consecutive bits. The eye will close up and the 0 and 1 levels will appear thicker and may even split. Now, Enritsu made a technical note that was very helpful in me preparing for this lesson, so I'm giving you a link to it because I'm going to be using quite a bit of their graphics. There's a picture of a perfect eye diagram. If we have a series transmission line discontinuity, undershoot in an eye pattern can be caused by either high impedance or low impedance line discontinuities. This example is more prevalent of what happens when a T-line is designed with an incorrect characteristic impedance, and therefore the source sees that series discontinuity. That creates a significant reflection, thereby causing signal distortion. So again, we have this Diagram on the left is what we're supposed to have, but because we have a series discontinuity, we have a major reflection of our input waveform. This is what you end up seeing. The same transition behavior occurs at the discontinuity on the other end of the T-line when the load impedance is driven by an incorrect characteristic impedance. So if my load doesn't match my transmission line, you create the same thing on the other side of my transmission line. A shunt transmission line discontinuity. The I pattern below is caused by a shunt open stub that is 60 degrees long at a bit rate. The stub can cause overshoot, ringing, and oddities in the crossing point of the eye. The amount of distortion increases with the length of the stub. This stub of problem occurs mostly from via stubs, and we're going to talk more about this later on. The effect shown in S21 is a dip in the return loss at the resonant frequency of that open stub. Now, it is easy to see the effect looking at different pulse patterns. The right side peak-to-peak amplitude of a 1010 sequence is less than that of the side on the left side being a 111000 sequence, because the 1010 pattern has more high frequency content than the left-hand pattern. And why is that? That's because this pattern is actually a waveform that goes high, 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 low, low, low. So it's a square wave of 1/3 of the frequency of this pattern. That means that the content of this pattern is going to be 3 times higher in frequency. Therefore, more of it is going to be attenuated by a cable. Even if the T-line has a correct impedance, S21 loss can also come from shunt capacitance or series inductances. They will also cause distortion of the eye diagram. The shunt capacitance opposes fast voltage transitions and will slow down the rising and falling edges of a data pattern. The degradation will have an exponential response with time constant tau equals RC. So let's take a 50 ohm load with a 0.3 picofarad parasitic capacitance that produces a 15 picosecond time constant. You can see that effect right here. A series inductance will have a similar effect as it opposes fast current transitions. In this case, we took the same 50 ohm load and we put a 0.75 nanohenry parasitic inductance. It produces the same 15 picosecond time constant. Again, if the T-line has a correct characteristic impedance, S21 loss can also come from other things. Dielectric materials have different loss tangents. The loss tangent quantifies the attenuation that the material causes. When you pick out a board material, whether it be FR4 or Rogers 4003, whatever it may be, each one of those has a loss tangent, and that loss tangent is also based upon frequency response. So you just need to be aware of that loss tangent is going to cause attenuation of your signal. Now, for example, when using programs that give a characteristic impedance based upon dimensions, only dielectric constant is used. While this may give you a correct T-line dimension, it does not show you the effect of the loss tangent for a particular material. Higher dielectric constants keep more of the fields in the substrate. While this can be advantageous in some respects, and specifically I'm thinking of like radiation purposes, it can be a problem if the material has a high loss tangent, because the more you keep the fields within the substrate with a higher dielectric constant, there's going to be more loss, and therefore the higher loss tangent compounds the problem. There's also other ways that you can have loss. You can have losses from non-continuous ground planes. When there is a non-continuous ground plane in a single-ended structure, then the effect is adding a series inductance. That series inductor is going to implement a low-pass filter. It will cause reflections because of the change of impedance of the structure. Now that we've explained the concept of how important a low-pass filter is to your thought of how it passes signals on a transmission line, to get you a handle on how does it affect specific types of protocols. I've got this chart in here that was created by Tektronix, and there's a reference there for you to get it. But I want you to take a look at like SATA 2, the 3 gigabit per second signal. Its fundamental clock frequency is only 1.5 gig. It's high, but not so bad in of itself. But notice the third harmonic gets to 4.5, and now the fifth harmonic is 7.5. 7.5 is really getting up there. Keep in mind, when you're talking about these frequencies, you have to keep in mind that any structure that gets close to being on the order of magnitude as the wavelength of frequency of interest, you start creating all kinds of little nuances of how that circuit's going to work. Now, let's look at USB 3 Gen 2. That data throughput is 10 gigabits per second. So when you do that, come down here, the fundamentals at 5, but look at the fifth harmonic. It's all the way up to 25 gigahertz. Now, anybody that's done any kind of RF work knows 25 gigahertz gets attenuated very easily. So that's one of the reasons why so many people have problems with high-speed design at these really fast data channels, because they're not thinking about how important it is to have these super high frequencies available and not be attenuated. In transmission line design, rarely are shorts encountered. Most problems stem from opens. As a signal propagates from the source down the transmission line, and there is a structure where the signal can propagate and see an open, then that open will reflect all of the signal. These portions of any structure are called stubs. You might ask, how in the world does a stub exist in a T-line? And that is a great question. The majority of stubs come in the form of vias. Not always, but majority of the time. In the example on the right, we have a USB connector that has to be soldered to a circuit board. If the signal trace leaves the pin on the top and stays routed on the top of the board, the result is an open stub created by the pin-via combination where the pin was soldered. So in this situation, my signal is supposed to come in the USB connector. It comes through this portion of the metal conductor, and it comes out this annular ring and gets on a trace and runs out the trace. We end up having the rest of this piece of metal acting as like a little miniature antenna, so to speak. It's a series inductor. And during this time, or this portion of the circuit, we also have capacitance that's distributed along here. Keep in mind, a transmission line, by definition, is distributed inductance and distributed capacitance. That's what you have on a smaller scale, is a mini transmission line for that section. With a normal T-line, you have what is shown on the right. The inductive and capacitive nature is consistent and uniform along the T-line. In the example with the USB connector, the signal trace staying on top of the PCB, that pin via creates an open-ended series inductor. It also creates a shunt capacitance along the length of the stub. Because if you remember, if we go back here, as this via exists in here, there's going to be ground areas here that are going to want to create a reference plane to the voltage that's trying to be created on the walls of the via. That is your shunt capacitance. The resulting equivalent impedance causes a resonance to show up in S21. Back a few slides, we talked about a practical transmission line known as a microstrip. In this diagram, you might notice that there is an impedance labeled ZS. That is your internal impedance of the source. Again, ideally, that impedance of the source is supposed to match the impedance of my transmission line, which matches the impedance of my load. But in some cases, this doesn't occur because the source impedance doesn't match the loads. Now, typically, drivers have a lower impedance. Well, if let's say you have a 50 ohm load out here and you have a 50 ohm transmission line, but your source impedance is only 20 ohms, well, then that's a problem. So in order for you to have maximum power transferred from the source to the load, you're going to want this source impedance to be 50 ohms. In this case, you would want to insert a series resistance on the output of the source to create a match. 9dots has a wonderful program to help with that. It's the ICD Stack-Up Planner, and it now has a new function included to help with that. If you pull up the program and you look on the second from the right of the toolbar, you're going to see a button right here, the red squiggly horizontal line. That starts a new program that we just added to this ICD planner called a termination planner. In the termination planner, you can either use an IBIS model that is given to you from your the driver manufacturer, and in it we can figure out what the internal impedance of that source is. If you don't have an IBIS model, you can use a generic model that this source has automatically installed, and you can look at the different types of generic source drivers. And let's say in this situation I'm going to route a UART line, and I know that that input impedance is or that source impedance is not exactly 50 ohms, but I know my trace impedance is going to be 50 ohms. I also know my trace is going to be 2 inches long, and I'm only going to have one load on it. It'll tell me that I need to put a series transmission or series termination resistor right outside the source, and that way it creates an impedance match to my transmission line. And if you have any desire to know more about this capability of this tool, please contact us. Thank you very much for this being here. Again, to summarize, I need everybody to understand that to really get good at high-speed design, you're going to have to think of the movement of energy or power as a wave, not just as currents like you did in low-speed designs. I hope you have the rest of your day is a great day, and here's Paul.
All right, everybody, thank you very much. Sean, thank you very much as well for that presentation. It's always amazing how much data we can try to push into an hour here. So you are here today because topics of this nature are very important to you. And let's face it, the industry has moved to high-speed designs, where I think in the last 10 years we talked about things moving from high-speed, from regular, I'll say, design speeds that have gone higher, right? Because we're always trying to push the edge there. But it's getting to the point where you really can't design without considering high-speed design. Even if you have a 10 megahertz device and you're using a TTL logic, those rising edges are so sharp now that they actually do have higher frequencies, as Sean has mentioned. All right, so first and foremost, who are we anyways? We are 9-Dot Connects. We are a PCB-centric organization dedicated to training, coaching, consulting, design, and layout of printed circuit boards. In short, we want to be everything when it comes to printed circuit boards outside of the actual manufacturing of them, but we want to be everything when it comes to knowledge. And we are there at that point. We have expertise in all of these areas. We do believe that PCB is the medium of all mediums. It's really hard to find anything out there that doesn't interface or somehow find its way onto a printed circuit board. You know, even the ASICs folks, as great as they can make things in silicon, all you're going to have is very structured silicon if it doesn't work on a printed circuit board. Even if you're doing cables, those cables are going to find their way to a printed circuit board. Circuit boards are just the medium of all mediums of electrical engineering. So what do we do here at 9-Dot Connects? We do quite a few things, as I mentioned just a moment ago, but I want to focus on coaching here for just a moment. And what is coaching? Coaching is really a block of hours for your PCB needs. And we can do it in different ways. For example, for Altium Designer, we can assist you in areas that may not be readily obvious or that a lot of people have wandered into. So for example, 2 weeks from today, I'm going to be meeting up with a customer who wants to know how to do cabling in Altium Designer. So I'm going to be coaching them on that. So these are the kind of things that we can do above and beyond the trainings that we provide on a continual basis. Also process related, so if you're trying to understand better how to do documentation, or if there's design flow, let's say the way you set up your schematics or the way you set up your printed circuit boards in general, we can assist you with that configuration management. Also, when it comes to design itself, if you're struggling with RF or you're not familiar with RF or high speed or power or any of these things you're just not strong in, come see us, right? That's why we put Sean out here today. Sean was kind enough to put this together to show our expertise to you. Okay? If you want more information, check us out at 9.connects.com. The thing we've done with this website is just not only put out what our products are, what our services are, we want to show you that we do have these expertise. We don't put anything out there that we cannot back. So contact us if you have any PCB issues whatsoever. Even if we can't do it, we're going to get you to the right individuals, okay? Because we're not going to take on something that we simply don't have the bandwidth or the skill set to do. It's rare in the PCB area that we would have such a shortfall. But if there's something they're trying to put together like an entire product or something that's more on a systems level, we can probably point you to the right people. But the fact of the matter is, use us first, discuss what you got first, and we can see what we can do for you. And with that, we are at the end of the hour. Thank you very much for joining us here today. Again, Sean.